In this video, I want to talk about measurement because in the last few videos, I sort of just started talking about quantum computing and mechanics, and I was throwing around this idea of measuring and observables in quantum mechanics, and I was sort of loose with the definition, and I realized that can be a kind of confusing concept. So I thought I would make a video to make it more mathematically rigorous on what I mean by a measurement. So just to recap, suppose we had some state of a qubit, and it's a two-level state, so it has two probability amplitudes, and we want to measure this state. And let me just draw this little measurement device because I'm going to be drawing it a lot, and this just means we're making a measurement. And this is going to take our state that's in either one or two configurations, and it's going to put it into either 1 or 2. And the probability that we get 1 here is the probability amplitude squared of the corresponding element, and likewise for 2. And this is just a refresher to understand, to see what's actually happening when we make a measurement. So it takes a probability amplitude of a state vector, which is our quantum state. We'll just call it Q for now. And it squares one of the amplitudes. So in effect, it kind of disrupts your quantum system. And what it does is it collapses it to a single value. And that's why I said in the other video that you want to be careful and you want to be clever when you choose to make a measurement, because it's going to completely disrupt your quantum state. And this is the nature of quantum mechanics, that actually measuring your state that you're working with has an effect on it. And this is unlike anything that we are familiar with in classical physics or in the everyday world. You know, you can make measurements without at all disrupting your system, but that's not the way it works in quantum mechanics, because these quantum bits are much more delicate, and a quantum measurement happens to completely collapse the state into one of its possible configurations. And this is the only nonlinear transformation that we can make throughout a quantum circuit. So another thing to note is that, well, in this case, in the case of a qubit, I mentioned that there's something called the computational basis. So we could have this vector here with 1 and 0, and this other one 0 and 1. But the choice of representing these vectors this way is somewhat arbitrary. The only thing that matters is that these two vectors happen to be orthogonal to one another. And it's useful in a mathematical description when you have two possible states to use orthogonal vectors to represent them. Because the thing about orthogonality is that these are as distinct as they could possibly be in terms of a two-dimensional vector space. So if you take the inner product of one with the other, which is a measure of how correlated they are, you get back 0. And if we want to talk about physically distinguishable states, it's fitting that we're using orthogonal vectors to do that. So when we build up this mathematical theory of measurement, there's a couple things we want. We want orthogonal vectors, and also we want real valued measurements. And I just say that because up until now, we're working with complex vectors and all these complex numbers, but we want the thing that we actually measure to be a real number, something that's more that we're more familiar with. And this is all things that you would have to take into consideration if you were building up the theory of quantum mechanics or quantum computing from scratch and trying to make it match with experiment. And this leads us into something called, well, first, let me just get this out of the way. An operator is, well, it's a matrix, or it's a way that you can act on a quantum state. So it's a linear transformation. And I just wanted to get that out of the way before I say this next part concerning these two criteria, there is a specific type of operator that happens to include both of these points in the actual information of this operator. So this is called a Hermitian operator. And Hermitian operators are just a neat way to package all of these criteria into one little object. Namely, let me actually first say what a Hermitian operator is. So a Hermitian operator is a transformation that meets the following requirement. So if we call it H, we need H to be equal to its conjugate transpose. So H is equal to H dagger. And this is the definition of a Hermitian operator. And a fact about these operators is that all of their eigenstates, all of their eigenvectors are orthogonal. So if we have this eigenstate 1 with some eigenvalue, and we also have this other eigenstate with a different eigenvalue, then we know that the inner product between these two is 0. And furthermore, another property of Hermitian operators is that these eigenvalues have to be real. They have to be real numbers. So just like that, we've sort of described this mathematical object that meets both of these criteria we laid out here. So it's nice that we can actually represent observables and things that we can measure simply by a Hermitian operator, because we know that the eigenvectors of this Hermitian operator are going to be orthogonal to one another. So those would be the actual configurations of our quantum state. And then the eigenvalues corresponding to each of those eigenvectors are going to correspond to what we could actually measure, to the actual measurement values we're going to get per state. So this will be useful to us in the following videos. And I just wanted to get it out of the way before I started talking about these Hermitian operators, and just so that there's a little bit of intuition behind what is actually meant by this. And in the next few videos, I want to introduce a very important set of Hermitian operators that also happen to be unitary, called the Pauli operators, or the Pauli matrices. And these consist of 3 matrices labeled X, Y, and Z. And they're pretty special. We're going to go over why that is in the following video. Thank you.